This is the idea that unlocks principal component analysis, PageRank, and the stability of systems. It sounds intimidating, eigenvectors and eigenvalues. But the picture behind it is genuinely simple, and once you see it, you will never forget it. Apply a matrix to a vector and in general, two things change: its length and its direction. The arrow gets knocked off the line it started on, pointing somewhere new. Try direction after direction, and almost everyone gets deflected. The transformation twists the whole space around. But for most matrices, there are a few special directions. Vectors that, when you apply the matrix, do not get knocked off their line at all. They keep pointing exactly the same way, only their length changes. These rare, direction-preserving arrows are called eigenvectors. The word eigen just means the matrix's own. Since an eigenvector keeps its direction, the only thing the matrix does to it is scale it. Stretch it or shrink it by some fixed factor. That factor is the eigenvalue, written lambda. An eigenvalue of 3 means the eigenvector triples in length. An eigenvalue of 1 means it is left completely unchanged. This gives us the defining equation of the whole subject. A times v equals lambda times v. On the left, the full matrix transformation. On the right, just multiplication by a single number. For an eigenvector, the entire matrix acts like one plane scalar. That is what makes them so powerful. How do we find them? We rearrange the equation, and it turns out an eigenvector can only exist when a certain determinant is 0. Setting the determinant of a minus lambda I to 0 gives the characteristic equation. For our example matrix, it factors neatly and the eigenvalues fall out, 3 and 1. Now the payoff on screen. Sweep a candidate arrow around the circle. Most directions get deflected off their line. But along the diagonal 1, 1, the output stays perfectly on the same line, an eigenvector, stretched by 3. And perpendicular to it, another eigenvector left unchanged, the matrix's hidden skeleton revealed. Here is where machine learning cashes in. Take a cloud of data and compute its covariance matrix. The eigenvectors of that matrix point along the directions of greatest spread, the axes the data naturally lives on. This is principal component analysis. Rotate onto the eigenvectors, keep the biggest ones, and you have compressed the data while keeping its essence. And it does not stop there. PageRank finds the eigenvector of the web's link matrix to rank every page. Engineers use eigenvalues to test whether a bridge or a system is stable. Physicists find the natural frequencies of vibration. Everywhere a system has natural directions, eigenvectors are how we find them. So, eigenvectors and eigenvalues. Eigenvectors are the special directions a matrix leaves on their own line. The eigenvalue is how much it scales them. A times v equals lambda times v. They reveal the hidden structure inside any transformation and power PCA itself. That completes linear algebra. Next, we turn to the shapes of space, geometry, Chapter 9, Distance and Norms.